Okay.
That's as close as it's
Sorry
going to
about
get.
that. All right, so I've now reclaimed everything. So welcome to 383 Complex Analysis. This is lecture 5, and what I want to do today is talk about the primitive theorem and Cauchy's theorem. There probably won't be much time to get to Green's theorem today. So hopefully this is good. And I've got another iPad set up so I can see that the slides are making it. And I will be monitoring the chat in case anybody has a comment that I am not hearing from the audio. Okay, so the first thing is we said that complex analysis loves to use different words for concepts we've already heard of. So we like to use the word primitive rather than antiderivative or an integral. And so the primitive is just a function whose derivative is the function we're looking at. And so the big result for today is Cauchy's theorem. And for our counters, that's another +1 for Cauchy. If f is holomorphic in a disk, then the integral of f along any closed curve in that disk is 0. And the proof is very straightforward. We already have that if a function has a primitive, then the integral over any closed curve is 0. That was corollary 3.3 of chapter 1. And so the key fact here is that if f is holomorphic, then it has a primitive. The nice corollary is that if f is holomorphic in an open set containing a circle C, then this integral is 0. This is basically what you would expect. All right, and so here, you just have some picture. Here is our circle, and we have some curve, gamma inside that circle, and we are looking at integrating f over that. So the integral of f over this curve gamma, and we've talked about how you would do that by parametrizing things. All right, so let's actually do some integrals. So let's integrate z to the n about a circle centered at the origin. So we can write z as x plus iy, or more usefully, or z is r e to the I theta. And the second is the polar, and it's going to be 0 less than or equal to r, and 0 less than or equal to theta, say less than 2 pi. We do have to be careful because there is one point where there is not a unique representation of it as r e to the I theta. Does anybody know which point that is?
0.
0. So in fact, all theta would work for that. So let's look at the integral about, let's say, c sub r of the function z to the n dz, where c sub r is a circle of radius r centered at the origin. So we can parameterize our curve. If we want gamma of t, would just be r e to the it, or r cosine t, r sine t, if you want to look at it as something in 2 dimensions. Well, rather than using t, what letter would we probably use instead?
Theta.
Theta. So let's use theta instead of t. So gamma of theta is r e to the I theta. What would gamma prime of theta be?
IR.
So it would be I r e to the I theta. And we're using, e to the z is the sum and goes from 0 to infinity, z to the n over n factorial, differentiate term by term. We have a way of defining what does it mean to take e to the I theta, and that series converges for everything. So if z is r e to the I theta on the unit on the circle of radius r, then dz would be I r e to the I theta d theta. And so the integral along the curve of z to the n dz would be the integral theta goes from 0 to 2 pi. We'll have r e to the I theta to the n, and then dz is going to be I r e to the I theta d theta. So this is going to be the integral theta goes from 0 to 2 pi of r to the n plus 1, I can pull out the I, and I'll have an e to the I n plus 1 theta d theta. So this is the same as I r to the n plus 1. Integral theta goes from 0 to 2 pi. And then e to the I n plus 1 theta, this is just going to become cosine n plus 1 theta plus I sine n plus 1 theta d theta. So what's the integral of cosine or sine if I go through an integer number of periods? So what if I integrate cosine of theta from 0 to 2 pi? What would that equal?
0.
0. What if I integrate cosine of 2 theta? That's also 0. Any integer multiple of cosine, inside the argument, cosine 2x, cosine 3x, cosine negative 5x, those are all going to integrate to 0. There's only one time when it's not going to equal 0. There's only one integer when it doesn't equal 0. Does anybody know what integer that is?
0.
0. And so when would n plus 1 equal 0? When n equals negative 1. So if n equals negative 1, we have the integral from 0 to 2 pi of just 1 d theta, which is 2 pi. If n is not negative 1, we have 0. So the answer, when n equals negative 1, the r to the n plus 1, that just becomes r to the 0. So it's going to be 2 pi I if n equals negative 1 and 0 otherwise. So we can integrate z to the n when n is any integer. And it's 0 for every choice except n equals negative 1. This is one of the most important facts in all of complex analysis. One of my professors at Yale, Serge Lang, once said if the Greeks had been very intelligent, rather than discovering pi, they would have discovered the constant 2 pi. And so there is actually a name for the constant 2 pi. Does anybody know the name of that?
Tau.
Tau, very good. And so some people celebrate 628, which is Tau Day, rather than Pi Day. And so this is one of the key facts that we're going to be using again and again and again. But we've at least now done one integral. When we were looking at Cauchy's formula, if f is holomorphic, then f has a primitive. We're going to show that soon. This is what we're going to try to prove today. Then the integral of f along a closed curve is 0. But it's very important that the function be holomorphic in the entire open set. So it's not enough to be holomorphic on the curve and maybe a little bit inside the curve and a little bit outside the curve. It's got to be everywhere. And so here are a couple of contours, and you might have seen something like this if you had done Green's theorem, is maybe my function has poles at some of these points where the function blows up. And so if I do something like this, my function is holomorphic here, and then it has poles here. And so the whole point of these contours is to reduce things to basically, is to reduce things. Is it no longer sharing the screen?
It's not.
This is why I have the iPad, so that I can see technical failures in real time. And so this is why we have contours like this. Is the goal is we reduce our space to two parts. One part where the function is holomorphic and everything is well behaved, and then one part where things blow up. And where it blows up, we draw small little circles about where it blows up. And the idea, and again, we're going to just play real fast and loose with the mathematics. Imagine, f of z is the sum n goes from minus, say, n to infinity of an z to the n. Then the integral along a circle of, say, radius capital R centered at the origin of f of z dz would be the integral over the circle of the sum n goes from minus n to infinity of an z to the n. And say only place f explodes is at z equals 0 if n is greater than 0. So what would you like to say the integral of the sum is? So
The
what's
sum
the
of the integrals?
Yeah, the sum of the integrals. Let's just switch the order. So n goes from minus n to infinity of the integral of, I'll put the an here, of z to the n dz. But we just saw that there's only one value of n, and that's when n equals -1. So then this would just become 2 pi I a -1. So if we have a function that blows up at just one point, this is what we're eventually going to show, is that if it blows up at just one point, the value of the integral is just 2 pi I times the negative first term in the expanded Taylor series. If the function has multiple points where it blows up, you just draw something like the multiple keyhole, and that's why this is one of the most useful contours there is. And you reduce everything to these small circles. And if you think about what's going on, if we travel along the outside, we then come here, we go around the circle, and we come back, we keep going around, come up, go around the circle, and come back. As we take the limit as that little distance between the two straight segments, getting to the circles goes to 0, those two will cancel each other out. And it'll reduce to integrating over the outside is the same as integrating over these different circles. So that's where we're going at the end of the day. So what we need to do now is we need to prove, that if we have a holomorphic function, then it has a primitive.
You can't see.
I'm trying to restore it. Is it back? Yep, okay. So a holomorphic function in an open disk has a primitive in that disk. That's what we're going to try to prove right now. So here is my open disk. Here's the origin. And then let's take some point here, z. And then what I'm going to do is basically use the Manhattan metric. I'm going to go east and then north to get to my point. So I'm always going to take that as my path. Okay? And I'm going to define f of z to be the integral, and I need to give this path a name. I'll call this gamma of z. So it'll be the integral over this path gamma of z of f. Okay? So I can write maybe f of w dw. So I have told you which path we're integrating over. It's possible I could have chosen a different path. I'm only looking at this path. If I choose another point, z plus h, then by definition, I have to go over and then up. And that would be the path gamma of z plus h. And so we would then get f of z plus h is the integral over the path gamma of z plus h of f of w dw. All right, so we're trying to show that big F is the primitive of little f. So let's consider big F of z plus h minus big F of z. What do you hope that this is approximately equal to? Couldn't quite hear you. What was that?
0.
Well, it will be approximately 0 if h is 0. So let's do a little bit better than 0. How close should it be to 0? What should it be differing by?
F multiplied by H. Small
Yeah.
f.
So this should be equal to f of z times h plus small. And that's what we need to show. We want to show that f of z plus h minus f of z. All right, well, if we look at f of z plus h, we first go like this, and then we go up. And then if we subtract f of z, we see that the part from 0 to the part right below z cancels each other out. And so just drawing what we have as a net, we have 0 over here, we have z, we have z, we have z over here, and then we have z plus h over here. And so we're going to have this over here, then we come up to z plus h, and we have this part coming down like this. Does everyone agree that those are the only 3 segments that survive? That the other segment is canceled? Yes? Everybody happy when we look at the difference in the integrals, that this is the contour that survives?
Yes.
Okay, okay. So now, does this look at all like any shapes we know? What regions do we know how to integrate a holomorphic function and get 0?
Rectangle.
Rectangles and what else?
Triangle.
Triangles. So let's add an integral in this direction, and then of course we have to add it in the other direction. And now we have a giant rectangle. What's the integral over that giant rectangle?
0.
It's just 0. And so this reduces to, now I've got my z over here, I've got my z plus h over here, and I've got this and going up. Can you think of anything I can add now?
Like an edge, and then it's going to become like a triangle.
Yeah, so if we put in an edge like this and go in both directions, we can use Gaussat's theorem. So we use Gaussat again, and we get that it's just enough. Oops. So here is z, here is z plus h. So it's enough to just look at the integral from z to z plus h along that curve. By Gaussat's theorem, everything else cancels. Okay, so now we get big F of z plus h minus big F of z is going to be the integral, let's call this eta of z of f of w dw, where here is z, here is z plus h, and here is my path, and I'm just going to call that path eta of z. I don't want to use gamma because gamma has already been defined as being this explicit curve from 0 to z. So it's enough to study this. Okay, well, if eta is the path from z to z plus h, and it's just the straight line and h is very small, then my function, my integrand, doesn't change that much. So what is f of w approximately equal to on eta?
F of z.
Good. Along eta of z, we have f of w is approximately f of z. Well, can we do a little bit better? how much is it off by? So what are we assuming about f? F is
Holomorphic.
holomorphic, so it's differentiable. So I could write plus f prime of z times how much I've moved, which is w minus z, right? Plus something small times w minus z. So small that when I divide by w minus z, this is going to tend to 0. And this is because f is holomorphic in a neighborhood of z. It turns out we actually don't need that. It's enough to just do f of w is f of z plus, let's do c of z. No, sorry, let's do c of w. Where c of w goes to 0 as h goes to 0. For all w on this curve eta of z. So this is just continuity.
Don't we have to say that CW over W goes to 0 instead of just CW?
I think might just be enough to say that CW goes to 0.
Thank you.
So let's find out. So this is just because f is continuous. So let's now integrate over eta of z. Let's see if we need more. F of w dw. That's going to be the integral over an eta of z of f of z dw plus the integral over eta of z of c of w dw. So for the first one, we're integrating with respect to what variable? So what's the variable we're integrating with respect to?
W.
W. What function, as a function of w, has derivative f of z?
FZW.
F of z times w. So this piece is just going to be f of z times w evaluated at z plus h and z. Right? So this piece is just going to be f of z times h. Now let's look at the second piece. So in absolute value, this would be less than equal to the maximum over w along the path eta of z of c of w times the length of eta of z. What's the length of eta of z?
Absolute value of h.
Absolute value of h. So this is going to be less than equal to the maximum of w in eta of z of c of w times the length of h. And we know that this is going to go to 0 even when we divide by the length of h. So f of z plus h minus f of z divided by h, well, that's going to be f of z plus h over h, that's going to just be f of z plus an error of size at most the maximum w in eta of z of c of w. And what can you tell me about this error?
That's a 0.
Yeah, goes to 0 as h goes to 0. And that proves the function big F is differentiable with derivative little f. So there's a great question or comment or concern, whatever word you want to use, that do we need to say more about how quickly this function c tends to 0? Or was it enough to just say that I can write it like this? And this looks like I didn't need to use the fact that little f was differentiable. This should worry you.
Well, we use it for the rectangle and triangle.
Excellent. So you found that very quickly. So we did use the fact that f was differentiable. We used it twice when we used Gaussat to reduce and say the integral over the rectangle is 0. Then we used it again when we used Gaussat to say the integral over the triangle was 0. Right? We've clearly used that the function is differentiable. But at this point over here in the proof, do we need to use the fact that f is holomorphic? No. It's nice that it's holomorphic, but all we need at this part of the proof is continuity. So the question then becomes, is it essential that f is holomorphic in this part? Can anybody give me an example of a continuous function that's not differentiable? Or at least a candidate for a continuous function that's not differentiable.
F of x
Maybe
equals
the-
to absolute value of x. Oh, sorry about that.
So you said f of x goes to what was the suggestion?
The absolute value of x?
Okay, what is the absolute value function? And that's going to be continuous and not differentiable. Any other suggestions for a function that's not differentiable but continuous?
Conjugation.
Conjugation. So what I would suggest you do is try to see if you can define a primitive for the function that's either the absolute value of z or the complex conjugate of z. See if this works. What do you think the answer is going to be? Do you think it has to fail if we try to put in, say, the complex conjugate or the absolute value? So what are your thoughts? So do you think if I put in the complex conjugate function, do you think it's going to have a primitive?
Probably not.
Well,
I think no.
if it has a primitive, the primitive has to have a derivative, right? So right now we don't know that a function that's differentiable once has to be differentiable twice. So it might be possible that if you put in the complex conjugate function, everything still works out. I strongly urge you to try to do that calculation. But what I want you to understand is the difference between necessary and sufficient. This is showing us that if we have a holomorphic function, then it has a primitive and then the integrals will be 0. But this is not saying that this is a necessary condition for the integral to be 0 along these closed paths. It's just saying it's a sufficient condition. So I strongly urge you to explore what would happen if you try, f of z is the complex conjugate of z, f of z is the absolute value of z. See if you can define a primitive, see if you get integrals over closed curves.
Wait,
Okay.
shouldn't it be paradoxic? Because
I'm sorry?
Because the holomorphism of a primitive is differentiable if the primitive can be differentiable, because like complex functions are infinitely differentiable.
Right, but we haven't proven that yet. We haven't proven that yet.
Okay.
Right. If we knew that, that would be enough to tell us that there's a problem, that we don't expect the absolute value function or the complex conjugation to have primitives, because we expect that there is this beautiful theorem that says if you're differentiable once, you're infinitely differentiable. But we don't know that yet. So whenever possible, it's good to get your hands dirty and do some calculations and get a feel for what's going on. So speaking of calculations, so here's a fun integral to do, the integral of 1 minus cosine x over x squared. And so to do that, I want to just quickly review some key facts. So we can write z as x plus iy, or z is r e to the I theta. Now, what do we mean by e to the I theta? We mean cosine theta plus I sine theta. Okay? So if I give you z bar, this is x minus iy, we can solve for x and y in terms of z and z bar. And we can solve for e to the I theta in terms of cosine theta and sine theta. So e to the minus I theta would be cosine theta minus I sine theta. And so with a little bit of work, you see cosine theta is e to the I theta plus e to the minus I theta over 2. And sine of theta is e to the I theta minus e to the minus I theta over 2i, if I've done things correctly. Yes. So what this means is, if I want to study cosine or sine, if I understand the exponential function, I can get cosine and sine from that. And in fact, the identities for cosine and sine, these identities are inherited from identities from the exponential function, which we will cover at some point later in the semester. How many of you have seen, has anybody here seen hyperbolic functions? So as an aside, the hyperbolic cosine of theta is e to the theta plus e to the minus theta over 2. And this is really like the cosine of the imaginary number times theta. So why is this useful? Well, let's say I want to integrate from minus infinity to infinity of 1 minus cosine x over x squared dx. The first thing you have to be careful about whenever you have an integral is whether or not the integral is well defined. So for this to be well defined, there are two concerns. Can anybody tell me what the two concerns are for this to be well defined? So what values of x make you worried? Everything's going to work out.
0.
0. So will behaved as x goes to 0. And what else?
Infinity.
Yeah. Decay rapidly as x goes to infinity. So fortunately, both of them are fine. Near x equals 0, we have 1 minus cosine x over x squared is like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus ... over x squared. The ones cancel, and you get x squared over 2 factorial over x squared plus, it's minus x to the 4th over 4 factorial over x squared plus ... So this is basically 1/2 minus 1 over 4 factorial x squared plus ... So it is well behaved near the origin. As the absolute value of x goes to infinity, we have 1 minus cosine x over x squared in absolute value is thus equal to 1 over x squared, and this is integrable. It decays fast enough so that it is integrable. So as x goes to infinity, the integral from, say, r to infinity of x to the minus, I'll say p dx is finite if p is greater than what? So for what values of p will 1 over x to the p or x to the negative p be integrable as x goes to infinity?
Is it 1?
Yep, as long as it's greater than 1. And so I'll leave you to do the exercise. If p equals 1, this is the logarithm, and it just barely diverges. As x is approximately 0, the integral, let's say, from 0 to epsilon of x to the negative p dx is finite. So what do we need here if we want this integral to be finite? So I think it's if it's less than 1. So if p equals 1, it's going to blow up. If p is less than 1, then when you integrate, I think everything's going to be fine. But you always want to get a feel for when is an integral going to be well behaved or not. And for problems like this, we have different behavior depending on where you are. Are you near infinity? Well, if you're near infinity, you must be decaying. If you're near the origin, you can explode, but you can't explode too rapidly. 1 over x squared is exploding too rapidly near the origin. But fortunately, we don't have that. So we want to integrate 1 minus cosine x over x squared. So the function does blow up at the origin, but it blows up in an okay way. So there are two possible ways we could integrate this. One is to replace cosine x with e to the ix plus e to the minus ix over 2. And then the other is we could replace cosine with e to the iz and just take the real part. I'm going to do the first method. So what we want to do is we want to integrate from minus infinity to infinity of 1 minus e to the ix plus e to the minus ix over 2 over x squared dx. And if we think about what's going on, here we typically go from minus r to r, and then we'll let r go to infinity. So this is going to be the same as the limit as r goes to infinity of the integral from minus r to r of, we'll say, our function f of x dx. Now this is where things get tricky. When we're near x equals 0, the whole function f of x is well behaved. We just showed that near x equals 0, it looks like 1/2. But if we try to integrate this term by term, then we're going to get some problems. So what you often do in a situation like this is you take a little bit of a detour. So what we'll do is we will come down the x-axis, and then we'll take a little bit of a detour, and then we'll continue coming along like this. And so this will be a circle of radius epsilon, which will be tending to 0. And so we're bypassing that point 0. Now, because our function f of x is close to 1/2, the contribution when we integrate over this small circle is going to be at most on the order of 1/2 times the length of that semicircle. So what's the length of the semicircle approximately? So what would be the length of the semicircle?
Radius times pi.
Radius times pi. So as the radius is going to 0, that's not going to be a big deal. And so what we can do is we can add this integral over that little bit of a bump, and it's not going to be a big deal. And then we're also going to add a big semicircle from minus r to r. And now we get this nice region. And in this region, f is holomorphic. So the idea is the integral of f over this whole region is 0. So there'll be 3 parts. We'll get the integral from minus r to minus epsilon of f of x dx, plus the integral from from epsilon to r f of x dx, plus the integral over the circle of radius epsilon, but actually it's not the whole circle, it's the semicircle, so I'll do s of f of z dz. Now, the last one is we have a semicircle going from r to minus r. From minus r to r of f of z dz. Okay? And this whole thing is going to equal 0. The first 2 pieces, what do these go to as epsilon goes to 0? So as epsilon goes to 0, goes to the integral from minus and r goes to infinity. This is going to go to the integral from minus infinity to infinity of f of x dx. So the first 2 pieces give us what we want. For this piece over here, for r large, f of z is what? So if we look at the complexification, it's going to be 1 minus e to the iz plus e to the minus iz over 2 over z squared. The z squared in the denominator is really good. How large is the z squared in the denominator going to be?
R squared.
It's going to be r squared, and the length of the semicircle is going to be on the order of r. So even when we multiply this by the length of the semicircle, that's not a problem. The problem is we have an e to the iz and an e to the minus iz. If we let, z equals I times r, so the point all the way at the very top.
I don't know why I did this so much, but I do.
So if z equals ir, then we have e to the minus iz is equal to e to the r, which is going to infinity. So the problem is, if we try to just integrate this directly, we have a problem because the term e to the minus iz is exploding. The term e to the iz is no problem. E to the iz is going to be at most how big? It's going to be most e to the ix, e to the minus y. And so the smallest is when y equals 0, so this is at most 1. So one of the terms is no problem. One of the terms is a huge problem. And so what we have to do is we're going to have to split this integral into 2 parts. And so this will be the last thing for today. So we have, something like this. And something like this. And so for this one, this is what we use to handle the e to the iz term, because the e to the iz term is going to be fine. And this is what we use to handle the e to the minus iz term. All right, I will leave the Zoom open in case anybody has any questions. If not, have a great day.